This video will cover Part 4 of Chapter 3, Sensation and Perception for PSY 110S, the Psychological Sciences. We're going to shift our attention to hearing. With this graphic from your textbook, you can kind of follow along the pathway that sound is going to follow as it comes into the ear. Sound is conducted through the ear by way of air pressure changes, essentially. After entering through the pinna, which is your external ear, the sound waves create vibrations in the eardrum that then move the tiny little bones that make up the middle ear. This movement leads to vibration of what's called the oval window, and that leads to movement of the fluid in the inner ear, which is lined with the hair cells, which are the sensory cells that eventually are going to transmit information, transduce that movement of the sound waves into neural signals. The movement of the hair cells creates those neural signals. They'll take into the primary auditory cortex via the auditory nerve, which also pulls in information through the thalamus. The outer ear includes the pinna, which is the external part of the ear. It collects sounds and then funnels those sounds through the auditory canal to the tympanic membrane. The tympanic membrane, which is also referred to as the eardrum, marks the boundary between the outer ear and the inner ear. The middle ear is made up of these physical structures. They're tiny little bones, the malleus, incus, and stapes, which are also called hammer, anvil, and stirrup because that's kind of what they resemble. They vibrate in reaction to sound waves that come in through the auditory canal. The stapes movement creates these vibrations literally on the oval window that covers the inner ear. The inner ear is made up mostly of the cochlea. The cochlea contains the basilar membrane that is lined by this large number, 16,000 hair cells, which are the receptor cells that are responsible for hearing. Now, if you imagine, if you went back a couple of slides to look at that image of the cochlea, it has this snail-like appearance. Imagine that you could unroll it and lay it out in front of you. It's like a reverse piano keyboard in a way. In an actual piano, you have the highest tones on the right, the lowest tones on the left. Well, flip it. So if we unrolled that cochlea, high frequencies would be at the beginning and low frequencies at the end. So you have that membrane that starts shaking the fluid that these cells are suspended in, and the higher frequency tones are going to make really fast waves through that fluid, influencing the early cells along the basilar membrane. Lower tones are going to have a slower frequency and travels farther down the basilar membrane. Fluid in that cochlea becomes displaced. It makes the hair cells move, and it causes what eventually becomes the sensation of hearing. There are a couple of forms of deafness. Actually, there are a lot of forms of deafness, but the two most common are nerve deafness, which is when hair cells or auditory nerve fibers are literally damaged. So the most common causes for nerve deafness are aging and persistent exposure to loud noise. So, for example, if you are a rock and roll musician who hasn't taken steps to protect your hearing during performances or practice, you may experience nerve deafness. Or if you work in a very loud workplace, like a factory with lots of noise, and you don't take steps to protect your hearing, you're likely to experience nerve deafness. Excuse me. One concrete example, there was an actor, I don't remember who it was, but they were being interviewed on a talk show and this was an action hero kind of actor who did a lot of gunplay in his films. And on his right side, he's right-handed. On his right side, he has almost complete nerve deafness in that ear and on his right ear because of the sheer number of times he shot a gun in the vicinity of that ear. So he's pretty much deaf in his right ear. There are lots of other examples as well. Pete Townsend, musician with the legendary rock band The Who, he's like in his 70s now. And when he was coming up, he's said this in interviews that nobody told them that they were going to lose their hearing if they didn't, use hearing protection. Nobody used hearing protection in the 60s when they played in rock bands. So by the time he's in his 40s, he's lost most of his hearing due to nerve deafness from just persistent exposure to extremely loud noise. Nerve deafness is more difficult to treat than the second kind of deafness, which is conduction deafness. Cochlear implants can be used to restore the ability to perceive auditory stimulation under nerve deafness. Conduction deafness can be caused by damage to the mechanical systems, damage to the bones, damage to punctures to the eardrum, and so on. So if those problems can be repaired, that's one thing. If they can't, hearing aids can be helpful. How do we determine pitch? And in some ways, this is analogous to what we talked about with vision, where you have complementary theories that combine to help us understand how we are able to perceive the full range of sounds that are necessary for us as a species. Pitch, just the word, refers to the quality of a sound as being high or low frequency and everything in between. Human beings, generally speaking, perceive sounds from 20 to 20,000 hertz. And that's our preferred range. We have evolved to perceive sound within those boundaries. Other animals have different windows, and they perceive sound differently. So, for example, I have this little device. It's an ultrasonic device that I use when my dogs are engaging in just way too much nuisance barking. I can push a button on this device that emits a sound that is so high-pitched, it's beyond that 20,000. I can't hear it. Now, my little device, it does me a favor. It has a little beep that's in my range of hearing, so I know it's delivering the sound. But my dogs can sure hear it. If they're off barking at whatever, usually it's nothing, and I push the button on the ultrasonic device, they all four of them just turn around and stare at me, and usually come back inside. For sure, they stop barking, which is awesome. But I can't hear that sound. On the other end of the continuum, you have animals like elephants and some of the marine mammals like whales who can perceive very, very low frequency tones that we cannot hear. They're just beyond our range. Now, the two theories that we use to understand pitch perception are place theory and frequency theory. Place theory assumes that there is a specific spot on the basilar membrane. Remember how I talked about unrolling the cochlea and there being a layout like a keyboard, like a piano keyboard in reverse, from high tones to low tones. So the assumption is there's a specific spot. It starts at the oval window, and each of the spots on that basilar membrane are going to respond to a specific frequency in order. The brain is going to know the frequency by knowing the location of peak activity along that membrane. So you start at the oval window, that's at 20,000 hertz. The pitch goes down reliably and predictably as you move down the basilar membrane. These peak locations tell the brain information about the frequency of the incoming stimulation. The frequency theory is built differently. It assumes that a sound that comes in is going to have a particular frequency. And that sound wave is going to be mimicked by the firing rate of the hair cells across the basilar membrane. So the example your authors give you, if the frequency was 100 hertz, the firing rate of the cells on the membrane would be 100 impulses per second. And what's being perceived by the brain as the frequency, if the brain knows the frequency, it's going to be based on the basilar membrane's firing rate, and that will be the determinant of the perceived level of the sound. As with vision, we have a composite theory. So if we have to look at the full range of sounds that we are capable of perceiving. Lower frequency sounds, so below 500 hertz, are going to be best explained by frequency theory. Higher frequencies that are above 5,000 are best explained by place theory. In between those two boundaries, between 500 and 5,000, both theories are in play. So when we look at both of those, then we can combine the information into a composite, and it helps us understand how we perceive sound. This means that place theory can help explain how we hear a range of pitches except for the low pitches. And frequency theory basically is responsible for how we make sense of those very low tones. There's also something called the volley principle. And this helps us for understanding, especially those high frequency tones where the cells are going to take turns firing. Cells will fatigue. If you had to fire 20,000 times per minute, it's going to get tired. So in a specific space, you'll have hair cells that are responsive to a given range of frequencies. They're going to take turns so that they can meet the threshold of what that particular frequency needs. And that concludes this part of Chapter 3.